I was indeed a participant at the very first MTTS, and it was a lot of fun and a long time ago now. But call out to Professor Kumaresan for making that happen. Thank you so much. Okay, so today I'm going to talk about reconstructing random geometric graphs, and this is joint work with Joseph Diaz, Tom Hayes, and Chris Moore. So what is a geometric graph? So you're given some convex subset of R squared, so think of a square, and you're given some endpoints in it, okay? And you're also given a threshold R, and we define a geometric graph to be one whose vertices are the vertices that we just picked, and whose edges, well, there's an edge between vertex V and vertex Vi and vertex Vj if the Euclidean distance between them is less than R, less than or equal to R, okay? And you may have heard of something called a unit disk graph. This is exactly the same thing when R equals 1. So here is a pretty picture. So we have 8 vertices here. They are you see 8 vertices. And how do you decide where there are edges? Well, say you look at this vertex, and then you take the radius R disk around it, and whichever of the other vertices are in there, you add the edges. Okay, so this is how you construct the graph. And so this is called a geometric graph with distance R. Okay, so what is, if you look at 2 vertices, right? Say V1 and V7. Well, what is the distance between them? Well, there's 2 notions of distance. One is the usual Euclidean distance because you've drawn this graph on a plane. So in this case, it looks like it might be about 2 point something. So V1 and V7, Euclidean distance is maybe about 2.6. Hopefully you agree. But then what is another notion of distance is the so-called graphical distance. The graphical distance means that you can't just go directly there. You have to go along edges of the graph. And then you look at the shortest path. Okay, so if I want to get from V1 to V7 in this graph, the shortest way to get there is through V8, and then V4, and then V6, and then V7, right? So the graphical distance is 4. Okay, so let me pause here and make sure that everybody understands these 2 notions of distance for a geometric graph, because that's crucial. So the Euclidean distance is just the distance that you all know and love. The graphical distance is when you aren't allowed to just go as the crow flies. Instead, you have to go along these graph edges. So it's kind of like, you know, when you're walking outside, you have to go along roads. So the distance is the shortest path. Okay, so why geometric graphs? Well, the first answer is, well, why not? We mathematicians will study just about anything, right? But another answer, for which I'm going to put my practical hat on, is this is a good working model for things like wireless networks or radio transmitter networks or things like that, where The vertices of the graph correspond to some devices, some transceiver devices, and the R corresponds to a transmission range. And then when is there an edge between two devices, between two vertices? It's when the two devices are able to communicate because they're within range. Okay, so that's one reason why geometric graphs are important. But now I'm going to take off my practical hat and go back to being a mathematician who'll study anything and say, well, why not geometric graphs? Okay, so the next question is, what is a random geometric graph? So I defined a geometric graph by saying, okay, you have some points in the plane, right? And then we use the underlying distance in the plane to define what the edges are. And now we've got a graph. Okay, so a random geometric graph is you start with some n, which is the number of points you want. And for simplicity, let's say that the convex set we're interested in is a square. And for technical reasons, because I want something called the density to be 1, I'll make it a root n by root n square. So it has area n. And what do I mean by the density is 1? Well, you'll see in just a minute. And I'm going to pick R to be between 0 and square root of 2n. Okay. And then I will sample n uniformly random points in the square. Okay. So here's a square. And I'll just choose some points at random. Okay. And then what are the edges? Well, I'll put in edges according to that threshold rule, which is that there's an edge between two of them whenever the distance is less than R. So, okay. So I'm gonna briefly stop and ask a question. Anybody see why I said R is at most square root of 2n? Show of hands. Am I gonna get any interactive participation here? Okay, I'm gonna treat that as a no. Well, the reason.
Hello.
Yeah. Hi.
Yeah. The R is strictly less than square root of 2n, so that we can fit the circle inside the square.
Exactly. So, well, not so much that you can fit the circle inside the square, but the point is the longest distance here is square root of 2n. So if I make R bigger than that, then basically every point will be adjacent to every other point, and that won't be very interesting, right? So that's why I want to take R that's smaller. And okay, so this is a random geometric graph. Okay, so let's get a feel for what such a thing looks like. So what about something like this? So we'll start with just what are the vertices? Can the vertices look like this? Anyone?
Yes, they can.
In principle, yes, they can. But here's the thing. If I sample n uniformly random vertices, then it is highly unlikely that I get all of them in this region and none of them in this region over here, right? Because any sampled vertex could be just about anywhere. So when I've got, okay, so for small n, it could happen that they all go to one side, but by the law of large numbers, once I've got a really large number of points in there, it's highly, highly unlikely that they would all go to one side like that. So this is not what it looks like. Okay. Now another question is, Okay, so when I put in n points and I said that meant that the density was something like 1, what that was saying is, sorry, what happened? Yeah. What I was saying is that on average, there's about 1 point per square unit of area, right? So do you think the graph could look like this? Again, yes, of course it could. You know, if you toss a coin 1,000 times, it can happen that you get 1,000 heads, but these things are extremely unlikely. So again, this is not what the graph looks like. Okay, so what does it actually look like? Okay, so here's the thing. If I have some set A in here, okay, then what is the probability that the point, a uniformly randomly sampled point, is in this set? Well, it's the area of A over n, right? It's how much of the area of A represents all the points that you could pick in A, and n represents the measure of all the points you could have picked out of. So if you pick a random point in the whole square, the probability that it lies in A is area of A over n. Okay, so if I'm going to put n points, how many do I expect to go in there? Well, the actual number that goes in there is, for each point, it could go in with this probability and stay out with the probability 1 minus that. And so the number of points that go in that set follows a binomial distribution. And its mean is the area of A. In other words, on average, you expect to get area of A many vertices in here, but the actual number could be something off from that by a few standard deviations, or if you want to look at very low probability events, it could even be something off by that by more, but that doesn't happen very often. Okay, so a couple of properties. So the number, what we just said is that the number of vertices in the set A follows the binomial distribution, and an expectation that is the area of A. So if you look at a particular vertex, right, how many neighbors do you think it has? Anyone? Well, when is a point going to be a neighbor? Yes, I hear somebody. No, I thought I heard somebody turn on their mic. Okay. When is a point going to be a neighbor? Well, when it's inside this circle, right? How many points fall inside the circle? On average, pi r squared. So maybe, okay, you have the fact that the v was there in the first place, so maybe you want to say it's pi r squared minus 1, but we won't worry about that. So how many neighbors does a vertex V have? On average, it has pi r squared neighbors. And finally, one other question of interest is, do you get a connected graph? Okay, well, if you've got a square and, you know, n is very small, then maybe you don't get a connected graph because points are far away. Okay. Also, if you have large n, but R is very small, R is so small, in fact, that say R is 1, right? Then you probably don't capture much in your circle of radius 1. And so you might get some little trees here and some little trees here and a lot of isolated vertices. Okay, but it turns out that with high probability, when R is big enough, that is, it's at least square root log n over pi, then the graph is very likely to be connected. And when R is smaller than that, it's most likely not going to be connected. In fact, it's most likely going to be a bunch of isolated vertices with some little trees. Okay, so this is the case of interest. In fact, we're really going to be interested in R even much bigger than that. And let me show you a picture. So here is what a random geometric graph might look like. Okay. The number of vertices here is probably in the thousands. Okay. So any questions so far?
Yeah, you said pi r square. Don't you need to divide by n for that? Because that's the area, right?
Yeah, so the pi r squared is the area, but the point is that so dividing by n was going to be the probability that a single point got in. But once you've done that n times and n points have that much chance to get in, on average, you get that many, you get pi r squared points.
Okay, okay. Yeah, okay.
Right?
Yeah.
So, okay. So now, here's the thing. Somebody sampled a graph that looked like this. And then they wrote down this adjacency matrix for the graph that looks like this. So what is an adjacency matrix? It's just a matrix. It's an n cross n matrix. And in column ij, you have a 1 if there's an edge between vertex I and vertex j, right? So here vertex 1 is adjacent to vertex 3, but not vertex 4, and yes, vertex 5, and so on, right? So somebody sampled this random graph and they wrote down its adjacency matrix. And then they took this nice picture, they've written down the adjacency matrix, and then they erased the picture. Okay, so we no longer have the coordinates. And most of the rest of the talk is about the so-called reconstruction problem, namely, can we get back the picture from just this adjacency matrix information, just information about which edge is adjacent to which other edge? Okay. Well, like all good computer science problems, this is NP hard. If you don't know what that means, think of it as code for computationally intractable. So our best hope is not to do it exactly, but to find, and by the way, this is NP hard, even if you know all the distances exactly. So, so our best hope is to find a good approximation. Okay. And putting back my practical hat on, well, why do we care about this? Well, it's an important problem to modeling the transmission of information in wireless networks. And by the way, if you think about it, you think about what this means. It means that if, say, you're talking about things like phone data, right? It means that phone data such as like where the phones are with, say, GPS or something, it means that even if you erase all the actual GPS data, just knowing which, sorry, phones is a bit weird because they talk to the cell towers rather than each other directly, but radio transmitters, right? Just knowing which one was able to communicate with which other one means that you can pin them down to location approximately, but fairly well. Well, what does this mean? It means that at some level, any sort of communications data that is out there about you, even if you think it's anonymized, there's a certain amount of privacy loss. Okay, so, all right, doom and gloom. Yeah, so in a way, the fact that we can reconstruct these graphs is sort of a negative result for privacy, but on the other hand, it's a good way to model how information moves in these big wireless networks. And as you see, there's a long list of papers there. Lots of people have worked on it, and most recently, me and my co-authors. Okay, so taking back my practical hat off, let's go back to the question. So how do we reconstruct? All we've got is this adjacency matrix, right, of some ones and zeros. Yeah. How do we even recover R? I mean, forget about the graph. Can we even recover what the threshold is? Well, the answer is yes, that's easy, because from this adjacency matrix, you can easily compute the degree of a vertex, right? What do I mean by the degree? The degree of a vertex is the number of neighbors it has. Right. So for each of these, for each of the V, I compute how many neighbors it has. And remember, that is something that is supposed to be pi r squared on average. So if we get a whole bunch of samples that are supposed to be pi r squared on average, then from that we can recover R, right? Because that's just how statistics is done. You get a whole bunch of samples which are supposed, so then you look at the sample mean. The sample mean is supposed to be pi r squared. So you divide it by pi and take the square root, and that's your estimate for R. And the weak law of large numbers or central limit theorem or one of those lovely things tells you that when n is pretty large, and we're really interested in the asymptotics here, so when n is pretty large, that average you get is going to be pretty close to R. So yes, we can recover R. Okay. Now what about actual distances? So remember, the graphical distance is the distance going along a path of the graph. And that you can calculate pretty easily from the adjacency matrix, right? So this is the graph distance, and you can calculate from the adjacency matrix. And this here is the Euclidean distance, right? So if we want to be able to reconstruct the graph, we need to be able to get pretty good estimates on the Euclidean distance, right? But on the other hand, the graph distance, when these points are in the plane, the graph distance might not go straight there. It may go back and forth. So so we want to relate these two quantities. And well, one direction is easy, right? Clearly, the Euclidean distance is at most r times the graph distance. Why? Because each of these edges was at most r, and there are that many of them, and if they were all exactly r, and in a straight line, that would be the Euclidean distance, right? And the Euclidean distance is providing a shortcut, so this direction's easy, okay? But how do you get a bound? How do you go the other way? So suppose you have your points U and V, and there is, we don't actually know where they are, but let's pretend that we did, right? And this is the line between them, right? Now, there's some random process that produced these points, right? So if I look at a sequence of convex lenses like this, okay? And each of these has width something of the order of r to the 1/3, and sorry, negative 1/3, and height r to the sorry. So each of these has width some epsilon and height some h, right? Then the area is going to be something that is like epsilon h, and if we make that thing area 1 or area log n, that it's very likely to have a point in there. Okay, so each of these disks, each of these lenses has a point in it, and there we've constructed a path, right? And well, okay, I guess I didn't tell you what the radius is. So these things are arcs of radius r/2, so that each of these distances are r. So once we've found a point in each of these lenses, it automatically gives you a path from here to here, right? And it turns out that we need to take epsilon equals r to the 1/3. And so that relates this distance, right? This distance here with the distance r, because these, okay, I'm not saying this very well, but what I'm trying to say is that because of, when n is large, because the way the distribution works, it's not that, these are your u and v, and then in order to get the shortest path, you have to go some very long winding thing. It turns out that you can choose your path, you can choose your points along the shortest path pretty close to this line and take pretty long steps so that the actual shortest path distance is not too many times more than the actual Euclidean distance. On the other hand, and this result was from one of the earlier papers, okay? But on the other hand, what's going on is, if you look at these segments of length r, if v was sort of just past the end of one of them, right? Then you're estimating, I mean, so what this tells you is that just r times the Euclidean, r times the graphical distance is a pretty good estimate of the Euclidean distance. But on the other hand, it can't be all that good, because if the v was just past this, right, you're definitely going to be off by something like r, right? Because you have to count this last interval as 1, even though it's just some small fraction, okay? So in other words, this error of r, well, first of all, this approach gives you an error of order r, but additionally, the error of order r might be fine when it's really long distances, when you're talking about points that are at this corner and that corner. But look at these two possibilities. If you want to distinguish them, here u and v are really, really close, and here u and v are not so close but still within r. Well, if you just say the Euclidean distance is an approximate count, an approximation of the distance, then you're going to do pretty badly, because both of these just look like they're at distance r, where in fact they're not, right? So how can you distinguish between these two possibilities? So so here is the sort of insight, which is that if you look at this symmetric difference between these two balls of radius r, right? So notice that over here, that's this very tiny thing, whereas over here, it's this very big thing. Okay, well, this is just geometry. There's some formula that relates the distance between the centers to the area of this lens, or to the area of the symmetric difference, right? And that's a formula that you can write down. Okay, so how does that help us? Well, the reason it helps us is that we have this property of these graphs, which is that a region of certain area must have that area worth of points in there on average, right? So what can we do? In order to estimate this distance, we simply, since n is large enough, we simply count how many other points fell in here and treat that as an estimate of the area. And then we invert this formula to get the distance, okay? So you should be able to see that because there's a tiny difference, there's a tiny area here, this thing will collect only a few points, right? And therefore, when you apply the inverse of the formula to it, you should get only a small distance. Whereas here, there'll be lots of neighbors of, okay, sorry, I guess I didn't say, how do we know whether a point is in here or not, just based on the adjacency matrix? Well, in order to be in here, the point must be adjacent to u. but not to V. And in order to be in here, a point must be adjacent to V, but not U, right? And again, you can count how many such things are there just based on the adjacency matrix. Okay, and once you've done that, you can apply the inverse formula to it, and you can get an estimate of this distance. Okay, so that tells us that we can get estimates of short distances, and what I'm not going to go into is all the proof about why this estimate is a good one, but it turns out that you can get these estimates, and they're, for large n, they're very, very sharp. In fact, the error in them is something that's much, much, much smaller than R. It's order 1, in fact. It's okay. So now we can do short distances really well, but for long distances, we might still have this off by 1 thing going on, where you take a full step in the graph, and that corresponds to a distance of R, but maybe you really wanted just 1/100th of a step, right? So how do you deal with that? The way you deal with that is you look at hybrid distances. So you have two distant points, U and V, and so now you look at all possible neighbors of V, and you look at the distances of U in the long range to all of those, and you look at the distance of V from W in the short range, namely this approach. And then you say, which of those is the minimum, right? And the idea is that the minimum is unlikely to be achieved by something that goes really out of the way, like say that, right? Instead, it's very likely that the minimum will be achieved by something that stays pretty close to the line between U and V, right? And so if you minimize this D1 distance plus D2 distance, then this gives you a pretty good estimate. And the error is asymptotically much smaller than the R that we care about. Okay, so that tells us how to estimate distances. So back to reconstruction. So we can estimate distances, but you know, how do we reassemble all of this back into a square, right? So one tricky part is that this stuff here involves looking at these, looking at how many neighbors are in this ball and how many neighbors are in this ball. And if those estimates, they don't really work well if you're close to the edge and your ball around your point goes out of the square like that, right? Because it gets skewed by the fact that there are no neighbors over here. So, so the question is, how? So in other words, in order to do this hybrid distance, you at least need this point to be well inside the square, right? So here's the square, and I have a list of points and I have their distances from each other. How can I tell whether a vertex is in this nice central region or whether it's in this iffy edge region? Well, I kind of gave that away already, because what is the property of this edge region that we don't like? Well, it's that if you take a point there and you take the ball around it, then, sorry, that's a bad picture here. Part of that ball is outside the square. And that exactly tells us how this is going to work, because points inside are going to have degree about pi r squared, whereas points on the edge are going to have degree that's smaller, corresponding to how much of the circle around them did not have any neighbors. And degrees are something that you can calculate from the adjacency matrix. So just by looking at the adjacency matrix, you should be able to tell pretty well which points lie in this region and which points lie on the edge. Okay, so here is how we're going to go about reconstructing. Okay, so I'm going to start out with my axes, and I have a whole bunch of information about which gathered from the adjacency matrix about all the pairwise distances between the points. Okay, so what I can do now is, because I'm able to find these pairwise distances, and because I'm able to find which points are in the center, and the pairwise distances are pretty good estimates, it means that I can go through this list and I can pick out 3 points that I know to be, that I'm pretty sure are inside the square, not near the edge, and which are also additionally roughly related to each other as an equilateral triangle, right? So I pick these 3 points and I simply put them down wherever I want, at the right distances, of course, right? Okay, now, once again, I have all these, so let's say that that's this point here, and this point here, and this point here, and I've just placed them on the plane. And how do I know how to place them on the plane? Because I know this distance, and I know this distance, and I know this distance. I admit that these are not exact, they're only pretty good estimates, but up to a pretty good estimate, I know these distances. And Euclidean geometry tells me that there's a unique such triangle. So I place them down. And then for each other point, right, I want to place that point down somewhere in the plane. So I say, okay, what is its distance to this? It's something. What is its distance to this? It's something. So let's say based on those 2 distances, I get 2 possibilities for this point here or here. Now, how do I decide whether the point goes here or here? Well, that's what the third landmark is for. I also have distances to this point, right? So if it's big, then I know the point went here. And if it's small, I know the point went here. So in this case, maybe it went here, right? So, and similarly, I have another point I want to place. And I know that it's distances from, these 3 things. So maybe it gets placed there. And I have yet another point I want to place, and I know once again the distances from these three landmarks, and maybe it gets placed there, right? So the point is, because I know all pairwise distances, I can now just do a little geometry using these three landmarks that were in the center, and relative to those, I can place all the points. Okay, so because these distance estimates are really good and everything is pretty rigid in Euclidean geometry, what I should get when I've placed all my points is a square. And I do. What's the problem? This square is not really axis aligned. So is this a problem? Not really. Once I've done that, I just take it and, oh boy, this doesn't let me turn it. Okay, well, as a mathematician, I can totally turn this in my imagination, but this program doesn't want to let me turn it. Sorry. Okay, so I can move it over here and then
maybe you could align the axis.
Right. I want to take this picture and I want to turn it so that the axes are aligned, and that would then give me my reconstructed square, right? My problem is that this program here is not letting me do that to the picture. So use your imagination, yeah? Basically, I want to align this axis and this with these axes, and then that would give me a square, okay? So to summarize the algorithm again, first we compute all the graphical distances. So this is a well-known shortest paths algorithm. Then we find three landmarks that form close to equilateral triangles. And for all the other vertices, we estimate the distances to the landmarks. And then we do an isometric embedding of all of this into a square, and we realign it. And having done all that, what do we get? We get a reconstructed we have reconstructed the random geometric graph. Except that we haven't quite, because back in this picture, I made an arbitrary choice that, you know, this corner of the square went here, but I could have just as well put this corner of the square here, or that corner of the square here, or that corner. So it should be pretty obvious that, like, this whole reconstruction, you can only do it up to the symmetries of the square itself, right? But up to the symmetries of the square, what we've shown is that we can reconstruct this random graph just from information about which matrix, which vertex is adjacent to which other vertices. And the kind of error we get is pretty small, right? So here is the main theorem. I guess, yeah?
I'm so sorry, but it's almost time.
Yeah, this is like the second last slide, so I'm just about done.
No problem. No problem.
So, yeah, so what have we shown? We've shown that for sufficiently large R, we can reconstruct distances and positions up to symmetry, and the error is asymptotically very small in R. And when R is even bigger, n to the 3/8, it actually turns out that the error is only about order log n. And so this picture shows what it shows is R is n to the alpha, and the error is n to the beta, right? And the previous results were in the range 0 to 3/14, everyone just gets large error, but the previous results were getting this error of approximately R because of that last step. And what we're able to do is get a decreasing error in this whole range and a very small error in this range. Okay, and finally, there was nothing special about the square. The same ideas extend to other convex sets or convex sets in higher dimensions or other manifolds, as long as you have some handle on the curvature. And I will leave you with this picture of the same thing working on a sphere. And thanks.
There's a question from YouTube. Manas Jana asks, by knowing which information of the original graph along with the adjacency matrix, we can surely reconstruct the original graph.
Okay, good question. So the thing about that, it's a question of what you mean by surely. So there's always going to be a certain amount of error that comes from all this randomness, right? And now, and moreover, computationally, it's even if you knew the distances exactly, it's a computationally hard problem to get sort of exact placements of everything. But so this fact that we get a good approximation rather than the exact thing, that's something you can't get around, you know, unless P equals NP and all computation falls apart and that kind of stuff. So this is a little bit of error in a little bit of jiggle room you can't get around. But there's the question of the symmetries, right? There's also the question of like, there's 8 different possible graphs you could create. And that you can pretty much get around if, say, you had 3 marked points, right? If you had 3 points where you actually knew the real coordinates, then from there, everything would just fall into place because then you would just choose those to be the 3 landmarks. I hope that makes sense. Okay.